We'll ignore the echo poll for now. So who's not from Triple E? Who's not from electrical electronic engineering, just out of interest? Okay, so we've got a fair few of you. So my name's Steve Griddy. I'm the module convener. There are two other people involved with the module that you'll meet later on. One is David and one is Alice, and I'll explain their roles in a few moments. But today is an introduction to the module. For those that have wandered in a few minutes late, I did mention earlier that this introduction probably encompasses about 25% of the examinable material. Okay? So even though it's an introduction, there's a fair amount of information that I want to try and convey this afternoon that's all quite important. So back to the teaching team. Steve Griddy, that's me. I will be covering the general information, robot kinematics, and as I said, I lead the module, so if you've got any issues with the module at all, the management of the module, the content delivered in the module, the teaching room, anything about it from an administrative point of view, then that's to come to me. If it's really topic specific, then that goes to the person who would be teaching you. And it's myself that will be in front of you for 6 weeks, then you get David for 3 weeks, then we have some revision sessions, and Alice will be looking after the coursework. Okay? So a bit about me, for those who haven't met me before. So if you're here from another department or you're doing an MSc, you may not have come across me yet. But I started here some years ago, back in 1998, undertaking an MEng in electronic engineering. Graduated in 2002, PhD in electronic engineering, and I've been here ever since, now full member of academic staff. My teaching covers a number of areas that are kind of related through my research. I look after in part the first year project module. Okay guys, can you keep it down and pay attention please? Okay. Where was I? First year applied engineering, so practical electronics, robotics. Third year robotics and AI, and advanced computing in year 4. Okay, so you may have seen me already through some of those modules. My research is in a kind of rather wide area of electromagnetics, and I'm interested in energy transfer through space. Essentially, and that's across every frequency in the spectrum from DC through to terahertz. So anything from interference that may propagate through the air through to wireless systems that provide data to your devices. I'm interested in the engineering side of those things, how to remove interference, mitigate interference problems, or look at how to improve the performance of wireless systems. Okay? So the majority of academics who teach are research active, so I'm also research active. So how does my research link with my teaching? So through my research, I undertake a lot of computational electromagnetics. So I use software, whether it's commercial software or software I've written to simulate large systems, and I make use of advanced computing techniques such as GPU computing to speed those simulations up, which is why I teach GPU computing in year 4. Experimental electromagnetics, I do a lot of experimental work. Some of that experimental work relies on robotics to allow me to probe areas and measure what's going on in areas of space, say over a circuit board, to see if that circuit board is producing interference. And I will design, make and use robots, either bespoke robots that I've designed and built, or off-the-shelf robotic systems to allow me to do those measurements. So that's kind of the tie-in between my research and my teaching. So, what are we looking to do through this module? So what you want to walk away from after this module is you want a knowledge of the types and applications of robots used in industry, knowledge of the components and structures, knowledge of components and the structure of robotic systems, knowledge of fundamental concepts in robot kinematics and control, the ability to derive homogeneous transformation matrices for multi-degrees of freedom robotic systems. So this is where we move into the more mathematical elements of the module. Ability to model the kinematic chains of robotic manipulators, ability to analyze kinematic chains, and ability to implement and relate theoretical analysis to physical observations, and that's where you will undertake the coursework that will allow you to put into practice the theory that I cover in this module. Okay? So how will this be taught? So lectures, material for the week ahead will be released ahead of the lecture. This is from my part. David may use a different approach when he starts teaching, if appropriate. What I mean by if appropriate today is a kind of a lengthy PowerPoint presentation. Typically, through the rest of the weeks, I will rely on handwritten in-class notes. So I'll use a tablet and I will write out what I need you to kind of learn in class. So in that respect, it's difficult for me to produce that up front. If that works for you, great. And the feedback I've had over the years of doing this, it works for people because it focuses the mind on working through the problems. If it doesn't work for you, let me know, okay? And I'll do what I can to adapt. But from lecture 2 onwards, I will move to handwritten notes. Because of that, the pace slows down a little bit, and it's easier to keep up with than just rattling through a set of PowerPoint presentations. It'll all be recorded. My notes will be provided as a PDF, and you'll have access to everything after the fact, so you're not going to miss out on anything. But if you do need to know, for whatever reason, what may be covered in the session coming, please let me know, okay? That's up to you to tell me. Otherwise, the notes you'll get directly after the session. So lectures, as we know, 3 to 5 on a Friday. So all material delivered and accessible through Moodle. So that's video recordings of the lecture, lecture notes, everything. Moodle page has a discussion forum. Say this every year. I would encourage all to use this to discuss both problems and any related topics of interest. To date, nobody has ever used it. And I'm happy to discuss the module outside of class, and it's a case of you just getting in touch with me via email or Teams, make an appointment, come in and have a chat if you need. So this is the overview of what we're going to do and when, always subject to a little bit of change depending on how much I talk rather than getting through the slides. But here we are, week 19, our introduction. We're going to move on to coordinate transformations. That's when we start looking at the mathematics. The mathematics is very simple. You should have all covered matrices or matrix algebra at some point. So that's the expectation here, that you know mathematics of matrix algebra, and that's it. And that's matrices up to the size 4x4, nothing greater than that. If you can handle multiplying 2 4x4 matrices together, that's probably about as complex as it gets, with some trigonometry thrown in as well. So coordinate transformations, homogeneous transformations, I'll explain all about these as we move through. We're looking at an algorithm for calculating the pose of a robot. So this is the algorithm you would apply in software. We look at inverse kinematics, which is another approach to working out how to pose a robot, depending on what you want to do with it. And then you get David for the last 3 weeks, either side of Easter, talking about dynamics and control. That's a bit more heavy theoretical-wise, but it's only 3 lectures, and that makes up David's 3 sessions cover 25%, little bit, probably 30% of the exam. So examinations worth 50% of the module. We'll cover all topics in the exam. All right, can you keep the noise down, please? Keep the chat down. All right, thanks. Examination will cover 50% of the module. The other 50% is 2 elements of coursework. Both courseworks worth 25%. The hand-in of the coursework is a short report, 6 to 10 pages max. That's all we're asking you to do. If you do 20 pages, you won't lose grade, you'll just be spending too much time doing it. And we'll give you some more information about the coursework as we move through the session. Okay, any questions so far? Anybody scared off yet? No? Cool. So before we start, so prerequisite knowledge, and this is assumed. I'm not going to turn this into a mathematics class. I'm not going to teach matrix algebra in this class. You'll be using matrix algebra in this class, okay? So I expect you to know basic algebra, trigonometry, and matrices, basic matrix algebra. Prerequisite knowledge, not assumed. Programming language, knowledge of a programming language might be useful to you when you come onto the coursework. It's not essential. We can teach you anything that you may need for that. And one approach to programming the robot to solve a problem, which is what the coursework's all about, is just using a linked building block approach called Blockly. You just join blocks together to get the robot to do what you want. So it's very simple, but if you have some programming knowledge, it will just help you in the way you think about that problem. And the coverage of that programming language will just depend on the experience within the classroom, and I'll come to that in a few weeks' time. And finally, and quite important, is imagination. We are talking about robots that operate in a 3-dimensional world. this is a two-dimensional view of that world. So with robotics, it really helps you to be able to picture how something's going to move in a 3D world, given my 2D drawing on the board. So if you can deal with that, this module becomes a lot simpler if you're able to just think how this thing would look in 3 dimensions. Okay? So, any questions before we're into the subject proper? No? Okay, so a bit of historical stuff. Robots, past, present and future. Before we start, what is a robot? So robot is derived from a Czech word, robota, meaning forced labour. And it's all about having something that you can control to do a piece of work for you. There are many definitions of what a robot is, depending on where you look. So Oxford English Dictionary will have one. The ISO standards will have one. Robot Institute of America will have another. But what we're really looking at is generally summarised in the bottom. And a robot is something that can sense its environment. From that information it gathers from sensing its environment, it can plan a sequence of actions or a sequence of moves, and it will continue to modify its actions based on things it senses to complete a task. Okay? So what we have is just a simple video illustrating this. So we have these robots will be equipped with sensors that kind of detect how much the arm is moving. Each limb of the arm is moving with respect to the other. Sensors that may be looking down at the conveyor belt to spot the shape, the colour, etc. of what is moving on the conveyor belt. So all that will come from sensors, whether on the robot or external to the robot. From the information received through the sensors, the robot will plan a course of action and will then act on that plan. So here the robot's looking to pick up shapes of a certain colour, sort them, etc. So it does that, sense what's going on, come up with a plan to reach, grab an object, and then act on that and actually perform that operation. Okay? So that's what we're looking at, a robotic system that's able to calculate something to do based on the sensors it has, do that thing to perform an act. Okay? So robotics is interdisciplinary in nature. And it's quite good that this module does attract people from other departments as well. So we have the electrical and electronic aspects of it, and that encompasses control schemes, hardware implementation, the sensors around the robotic system, the actuators to move the robotic system, so the motors, etc. That all comes under the umbrella of electrical, electronic engineering. Mechanical engineering, so mechanical engineers interested in the kinematics, so the motion of the robot arm, without considering how that robot arm might actually be moved by the motors. You just know it moves and you can understand how it moves. And the dynamics of that robot, so that's a study of the movement of the robot, considering any forces and or moments that you need to when that robot is moving. And then the computer science. Have we got any computer science people here this year? No? Okay. Computer science, stroke engineering. And that's all about kind of the motion planning, so deciding how to move your robot arm around objects, navigate around objects to reach what you want to reach, understanding the constraints placed on that movement by the actual mechanical aspects of the arm. So if I want to reach that bottle, I can't just go straight through the screen. I need to work out how to go around that screen, which is an object, etc. And also, robotic systems may rely on AI to design. So the computer scientists would come up with the kind of the brain of the robot. For me, I would use AI within my robot systems to identify components on a circuit board. And that's where I want to position my measurement device at a particular component. So I may use AI to do that. Okay? There's a lot of chatting. Can we keep it down? It's quite distracting, please. So, bit of fun. My kind of interest in robots stems from really science fiction and stuff I saw as a child. So I came across this, so I've stolen it. So these are a lot of the robotics, or a lot of the robots I came across became familiar with as a child. So if you're bored one evening, this is not examinable, but if you are bored one evening, you can go through there and see how many of these you might recognise. Okay, so some of them do date back quite far. Eek. Right, again, history of robots. This, again, is just here for interest. It's not examinable at this point. But pre-1900s, purely mechanical systems to do a job of work. You know, a lot of it was developed for entertainment, really, for fun factor. But then we moved on to kind of 1950s, where we had mechanical devices that were kind of programmed to do quite complex tasks. And then 1954, where we had the introduction of kind of truly electromechanical robotic arms. And then through to 1975, programmable universal machine for assembly, so Puma robot. Through to 1979, SCARA robot. I'm going to talk more about this as one of the examples of an industrial robot later on in the module. Through to more exotic robots that were kind of aware of their environment, so they could move around, sense what's going on around them, and react to that. Through to bipedal robots, robots capable of walking. Educational robots such as Baxter. Now, Baxter is a particular type of robot. It's a collaborative robot, which means it's safe to work in the presence of humans. So you could work next to a Baxter robot and know it wasn't going to strangle you, lift you off the ground, throw you through the window, because basically it doesn't have enough torque within its actuators to actually lift you or push you or hurt you. So it's a robot that you can safely work alongside. And there was an interest in a company just on the Boot site, but not too far from here, in having a Baxter robot work on one of its pharmaceutical packing lines to replace a couple of operatives, but it would work 24 hours in that role. So we'd have a human one side, human the other side. Human would kind of pre-fold a box open, Baxter would pack the box, and then the final human would kind of seal the box. But they were interested in using Baxter for that. Turned out to be pretty slow and not great at the task, so they stuck with the humans for that one. And then we moved to future robots, humanoid robots driven by developments in AI for manufacturing, domestic, education, entertainment, etc., and transportation. So there's a lot of activity in the area of robotics, okay? But for this module, we're going to focus on industrial robots. So, I mean, if you have an interest in robotics, you'll have seen over the last few years or more, then advances in robots have stemmed from using autonomous drones to deliver things. We have walk-in robots and able to cover quite complex terrain these days. More dexterous robots are able to really mimic what a human can do in fine detail. We have robotic systems used for industrial processes. So this is actually a research project here at the university, these two. And these are small, flexible robots that are basically worm-like, and they will find their way into a jet engine and look for faults within the jet engine, and if equipped with the right tool, will repair any issues with that jet engine. But the reason why we want something worm-like is because the inside of a turbine, jet turbine, is quite complex. We want to be able to weave through and control the movement of that robot. Okay, more cool robots. Bumblebee, unfortunately, we're not really going to look too much at that type of technology. But first question I wanted to pose to you, and this is how I was going to make use of Echo Poll, which is not going to work for me, is a car a robot? So let's have a show of hands. If you're thinking about autonomous vehicles, who thinks a car could be considered a robot? Based on what we've seen before, sensors, plan an action, act on the action. Okay, well, if we discount the people who are too shy to put their hands up either way, I think we've got a bit of a majority going towards a car is a robot. So, how do we determine if a car's a robot? It really depends on the level of autonomy, how autonomous that car is, how many sensors it has, what brain it has to plan a sequence of moves to perform a certain set of actions. The level of autonomy is defined under this SAE International list of autonomy levels, which ranges from 0 through to 5. So we go from no automation, driver assistance, so cruise control, automatic braking, partial automation, where we specify a drive-in mode, conditional automation, where the automation can control all aspects of the car when needed, not all the time. High automation, and that's when the driving mode is predominantly controlled by the system within the car, not the driver. And then fuller automation, and that's where you're the drivers or the passenger only in the car sat in the back seat asleep while the vehicle gets them from A to B, where they want to be. Anyone have a guess where I think we are now with this in general? You probably will find examples of all levels, 0 through to 5, but in general, where do you think we are? Okay, so we've gone from 2 to 4. I think it's probably around 3 we're moving towards. This time last year before, I probably would have said 2, despite what people like Elon Musk will tell you. I think we're hovering around 3 now with where we are with autonomous vehicles. Anything more than that, I think you find in quite niche applications, and they're quite restricted to where you find them. You won't find them. You won't buy a car that works anywhere in the world, for example, an autonomous vehicle. You might find one that works in a specific area that's designed for that specific area, and there's a set of legislation in place as well to govern the operation of that vehicle. That's another topic. So is a car a robot? I think we've kind of said yes. So, and the answer was maybe, and that's dependent really on the level of automation found within that vehicle. Okay, so these few next slides don't really work because the Echo Poll doesn't work, but I'll go through them anyway. So definition of a robot is a machine capable of carrying out complex actions automatically when programmed to do so and to respond on a set of external stimuluses. Components of a robot would be sensors, processors, actuators. So sensors on an autonomous car might have forward-looking cameras, might have LiDARs, might have distance sensors. The processing will be a compute engine within the car, compute system within the car, and you will have actuators that may control the steering, the braking, etc. So an autonomous car can have all components of the robotic system as we described so far. So autonomous cars can use those sensors to control motion. Okay. But just a couple of things to throw in. Robotics versus autonomous systems. While not every car is a robot, autonomous cars do fit in to the broader classification of a robot. Okay? So if it's very light on the level of autonomy, a car cannot be considered a robot. But in summary, an autonomous car meets the criteria to be classified as a robot because it's capable of perceiving its environment if it's at the correct SAE level. Make decisions and take necessary action. And then and on to another question, which we can skip because I've already answered it. It has to be at least, I think, SAE level 3 to be considered a robotic system. Okay, and in conclusion, we are a far way away from being at bumblebee levels of autonomy. So, all that said, so some of the impact of that has been removed because we can get Echo Poll working. So we can look at robots past, present and future. We have different classifications of robots that come into play. So we have stationary robots, so these are robots that do something, they're fixed in place. If this arm holding the monitor up had motors in each of its joints, it's fixed to the desk, it could move the monitor around under a set of control. That would be a fixed robotic system. Okay? We have wheeled robots, they're able to move around. Legged robots, able to move around. We have swimming robots, flying robots, modular robots, all forms of robotic systems. Things they have in common, they will have sensors, they'll be able to plan on a set of actions that are informed by the data gathered through those sensors. Hopefully this doesn't dampen your excitement on a Friday afternoon. We are only going to be looking at this class of robots, which are the stationary robots, which are typical of what you find in use in industry.
Do you remember this video clip of our robots working together using our superior motion control? If we didn't impress you with that clip, how about this?
So this is just an example of a few
What do you say?
robots working
Have you
together,
ever seen
and
an
they've been
industrial
programmed
robot
to
moving with such
basically,
outstanding motion
carry out
control?
a sequence of very fine moves.
As you can see, we've
each of
added
the trays
another
has a number
robot.
of cans on, separated
We've
by
also
just
tightened
more
up
than the
the
width of
tolerance.
the probe moving between them. The cans are not fixed to the trays either.
The distance between the cans and the pin has been reduced to an impressive 1 millimeter. And this isn't the limit of the robot path accuracy. It's the way the cans are mounted on the tray. How do we get this fantastic motion? By hours of programming? No way. Just program a path of combined straight lines and circles at normal slow programming speed. Note the three.
So the operator of this robot is going to plan the sequence of movements through a pendant that's connected to the robot. So they will instruct the robot to move through a set of coordinates, a set of predetermined moves. You're not going to get it that easy in this module. You're going to go through the mathematics to allow you to be able to program a set of moves into a robotic system. Okay? So that's the bit that's hidden from this illustration, is the manufacturer's made it easy for someone to control the robot.
Three robots moving
But we're gonna be
together
looking
when
at
the programmer
what
uses
is
the
underlying
joystick on the
mathematical
teach
theory,
pendant.
that goes along with that.
Then run the program in automatic mode up to full speed.
Having had enough of you. So a couple of illustrations. We have these robots working on an automotive production line. We have working on another production line that's manufacturing windscreens. These are static robots fixed in place. They don't move. Okay, they are there to serve that production line. But these robot arms also exist in wheel format, where they can move around an environment if you need them to accomplish a task. So we're going to move on to why use robots. This is kind of really where we start covering some of the stuff that will crop up in an exam. So why do we use robots? It's really to cope with increasing demands of dynamic and competitive market. Modern industrial manufacturing methods should satisfy the following requirements. So we don't use robots just for the sake of it. There's a number of things we need to think about in terms of our requirements that would justify the use of a robot. So we want to use a robot if we can reduce production costs. Can we increase productivity? Can we turn out more items that we're manufacturing? Can we improve the quality of those items that we're manufacturing? And that's where automation through the use of robotic systems can fulfill these requirements. Automation is not always the use of a robot, okay? So industrial manufacturing, there's three modes of industrial manufacturing, and that's manual labour, so humans doing some work, heaven forbid. Hard automation, and that's where we have an industrial process here that's fixed. It does one thing and one thing only, okay? So there's no intelligence within that system. If you need to do another thing, strip that back, remove it, buy a new one, okay? So that's how hard automation. So although we've automated something, that is not a robotic system. But we can use soft automation as well, where we use a robotic system to undertake the work for us. And this is a lot more flexible, hence the use of the word soft, is it will work on this automotive production line, but we could change the vehicle and it would still be able to cope with that. Okay, as long as it fits on the production line within the distance between the robots can be adapted, reprogrammed to work. You don't have to change the whole line. And this is an example of manual labour going on there. Okay, so three types: manual labour, hard automation, and soft automation. All have their uses depending on what you want to do. And it really depends on the setup cost of your industrial process and how many things you want to turn out through your industrial process. So if you have people working on a job, so one person can make one thing in 1 hour, etc. So the unit cost in terms of production volume is always fixed. Okay? So it always costs you the same to make one object, whether you throw more people at it or you give that person more time. The unit cost against production volume is always fixed. Okay? If we look at hard automation, that's okay for small quantities. Okay? If we need very large volumes of our coming off our production line, then we might consider hard automation. Because it requires a purpose-built setup to give you that automated process, It's quite a high initial setup cost. But the more units you turn out, the cost per unit will drop. Okay, so the more you make, the cheaper it gets. Okay, but it has this high setup cost. Now, if we look at soft automation, setup cost is slightly less. We can also reuse systems we might have in place. But again, the cost per unit will drop with the more we produce. Okay, so up to a point, good exam question, up to a point, manual labour cheapest, we're not producing too much. Then if we start producing a little bit more, we probably want to use soft automation that will run up to a point, and when we reach a certain point, hard automation becomes the cheapest per unit cost. Okay, so it really depends on how much you are producing. So again, quite cool for an exam question. So that's manual labour, hard automation, soft automation. Then you can combine manual labour with soft automation, which brings you to this collaborative robotic scenario that I mentioned Baxter would be useful in. Okay, so here we have an operative, it's positioned in the workpiece, and the robotic system is doing the riveting, the welding, the cutting that it needs to do. The human operative is there really just to position the piece in the correct place and observe what's going on. Okay, so they work alongside each other. The robots are specially designed so they can't generate enough torque, enough momentum, enough force to injure that operative, or they will work in a work envelope. I'll come on to that a bit later. Work envelope that doesn't cross over into that of the human operative. So this is an expansion of the previous plot where I have included collaborative robots in there as well. So cobots, if you have a human working alongside a robot, there's another kind of price point you can hit in terms of production volume. Okay. Right, okay, so it's a bit of background, why we use robots. We really want to use robots to make things easier, cheaper and better, but it's not always the best solution in terms of cost. Okay, so in terms of robotic systems, if you want to use a robotic system, you have to understand how the robot is configured, because that will determine what the robot can do and how well it can do it, and that's what I'm going to talk about now. So main components and structure of an industrial robot, and later on in the module I'll try to bring in some models as well and some things to illustrate some of the things I'm talking about, but at the moment try to keep in your imagination that we're working in a 3D world and think about how this may move in a 3D world. So we have a KUKA arm robot, so it has a base that's always fixed in place within an industrial environment. That doesn't move. Okay, that's important from our point of view. There will be an arm or a link on top of that base that rotates around the base. Okay, so I'll do a lot of this arm waving stuff as well. Then you'll have another link or an arm fixed to that, and there's a joint here that is kind of horizontal into the board. That's to another link. Again, you have another joint that's horizontal into the board, and at the end of that link or arm you have another set of joints, and that's connected, and that forms a wrist that's connected to whatever tool you may want at the end of that device. Could be a welder, could be a cutter, could be a spray painter, etc. So one way of thinking about this, the base is me, my feet are fixed to the floor, my waist is the first joint that allows me to move that way. Okay, this joint here then is my shoulder joint that allows me to move my arm kind of vertically up and down. The next joint is my elbow that allows that movement between these two links, and then the end set of joints is my wrist, which comprises in a fully capable robot. I'm trying to avoid some terms at the moment. A fully capable robot, there will be 3 joints within that wrist that allow you to point whatever's on the end, whatever's held at the end in any direction. Okay, so what you find is with this joint, and this joint, which are kind of my waist, my shoulder, my elbow, that allows me to position my hand anywhere in space that I can reach. Okay, so it allows me to position my hand anywhere in space. If what I'm holding in my hand, or what I have at the end of my hand, a tool, I want to orientate within that space. That's when the 3 joints in the wrist come into play. So the first 3 joints allow me to position the end of the robot arm anywhere in space, okay? And the 3 joints in the wrist, if you have them in the robot, allow you to orientate whatever is attached to that wrist, okay? Each joint has an actuator, so think of that as an electrical motor. For this purpose, I'm going to go on to talk about a few more examples of different actuators. So they make up the arm of the robot, so the arm or manipulator. I will use both terms interchangeably. If I say arm, it's the whole thing. If I say manipulator, it's the whole thing up to the wrist, okay? So the arm is every part of the robot really up to where the wrist is attached. And then we have the wrist, and then we have the end effector, which is a tool that will allow us to do some work. The whole thing, depending on the configuration, will have what we call a work envelope, and the work envelope is anywhere that the robot arm can reach. Okay, so that will have a limit on where it can reach, depending on the length of the joints, how the joints can move relative to one another. Okay, so robot configuration is determined by the set of rigid interconnected links, and so they're the orange elements in this. So link 1, link 2, link 3. So they're all rigid, they don't flex, they don't bend, so they're rigid. So the robot configuration is determined by those interconnected links. Links connected to each other by joints. Okay, so my forearm's connected to my upper arm via my elbow, so the elbow is the joint. End effector lies at the end of the final link, which I've already said, and the configuration will determine the work envelope where the robot can reach and work within and out to. Joints within a robot. There are many types of joints. We're only going to consider 2, and that is of a revolute joint. So a revolute joint is, think of it as, say, your elbow. It does one thing, it allows your forearm to pivot around your elbow relative to your upper arm, and it just does that. So it has one axis of rotation, which for you in this example is coming out towards you. That is a revolute or rotational joint. Okay, if you look at the monitor arm again, that is a revolute joint as well, because it only allows movement around that axis through the joint links. The other type of joint we're going to look at is prismatic, and that's a kind of think of it as a telescopic joint. So it's a joint that moves in and out of whatever it's attached to. Okay, so it has one direction of movement, telescopes out and back in. Okay, so again, I'll have some examples of these later on. There are other types of joints: screw joint, universal joint, spherical joint. Universal and spherical are all the more harder to analyze, so we're not going to go into those, and they don't feature that much in industrial robots anyway. A screw joint I may talk about, but that's just a combination of these 2. Okay, but the robots that we look at will be comprised of revolute and prismatic joints. Just some diagrams of what these joints may look like. So prismatic, we have essentially this element at the end will move along this center shaft on this prismatic joint, so it just has a linear movement. Revolute joint, as I said, is this link here will rotate around the end of this link around this axis. Okay, so again, think of the monitor arm if you're trying to picture that. Screw joint, universal joint, spherical joint, and we're not going to talk too much about. Actuators, now these create mechanical motion. Is it a bit hot in here? Yeah. Create mechanical motion, you require energy to create movement, and that energy can come from electric, hydraulic, or pneumatic. Okay, it really depends on the application and what energy sources you might have local to the robotic system. So for an electric system, energy is derived from current and voltage. Hydraulic, we're taking energy from fluid pressure, and pneumatic, we're taking energy from air pressure, changes in air pressure. Each have advantages, disadvantages. Electric actuators, so motors, they're good for high speed, good for very accurate movements. They're easy to control. The issue with electric motors could be if you're in a hazardous environment that may have flammables, etc. They can, generate sparks and ignite flammables, so you've got to be careful there. If they stall, if your robot hits an obstruction, it can't move and it's still trying to move, or it tries to lift something too heavy, you can generate a lot of heat as well. Hydraulic will give you modest speeds. A lot of power to weight ratio, high torque, safe in hazardous environments because you're only changing the pressure of hydraulic fluid. However, they're very expensive to maintain. If you get a leak, they're very messy as well, okay? But they're very good for things where you need to lift or move a lot of weight. Pneumatic, inexpensive, high speed, no pollutants. Air is normally available in most or not all industrial settings. The only issue is that air is compressible, so you may lose a bit of accuracy when you're trying to move a joint. They're noisy because of the pumps and the mechanisms that move using air pressure, and the air needs to be dried and filtered, otherwise you cause corrosion within your joints. So we got joints, actuators that move the joints, and they hold all our links together to give us our robot arm. And at the end of the robot arm, we have the end effector. So that's the tool connected to the final link. Can be a gripper to pick something up, can be a welding tool, spray tool, cutting tool, etc. Looking for a thermostat. And typically connected via a wrist joint to the remainder of the robot arm. And as I said earlier on, the wrist is responsible for orientating our end effector. Sensor systems, so the robot will be equipped with a number of sensors that will give us information that allow us to control the movement of the robot. So they will collect information from the environment and the drive units, the actuators on the robot, help make the robot intelligent. These are analogous to human senses of sight, sound, touch, smell. So a robot can be equipped with all manner of sensors to sense its environment. So the process flow you go through is the information collected is then used to be processed by the controller to instruct the robot how to move, okay? And a robotic system may use both internal, so sensors in the motor to detect how much current's being drawn, for example, so internal sensors, or external sensors that may be the form of vision systems, camera systems to detect objects need to be interacted with, or if someone, for safety reasons, was moving into the work envelope of the robotic system and that was dangerous, it would shut the whole thing down. Okay. So when controlling a robot, there are two approaches. One is point-to-point. So we use that for things that happen at specific points in time as well, such as spot welding or pick and place. So if you want to do a weld here, weld there, that's good for point-to-point. If you want to pick an object up and move it to another place, that is point-to-point is also good for that. So we're just working by going to a point, doing something, going to another point and doing something. Or you may want continuous path, and that's useful for things such as spray painting or laser cutting, where you want to move across a continuous path and do something as you're moving as well. Okay? So this video should illustrate both of those. So the moment that's continuous path, and that's cutting a shape out of a workpiece. And then we kind of incorporate a point-to-point control algorithm in there as well, where we go to a point, cut a small hole, move to another point, cut a small hole, and between the movements, the cutting torch is then kind of turned off. Okay, so that's kind of the links, which are the fixed mechanical bits, the joints between the links, the actuators, sensors that we talked about. We talked about the wrist briefly. We talked about the end effector, which is the tool at the end. These are all terms I'm going to use throughout the rest of the module. All those things together will enable a robot to have a specific work envelope. So that's the region, the volume that the robot can work within and work around. Okay, the work envelope is determined by the combination of the joints, and we're only considering robots with prismatic and revolute joints. Okay, so the work envelope is determined by the combination of those joints, prismatic and revolute. The more revolute joints you have in a robotic system, the more complex it becomes to analyze. Okay? And some of the examples I will show will demonstrate that. If you have something that's just prismatic joints, which is this, so 3 prismatic joints arranged on X Y, Z axes will give you a range of motion, give you a certain work envelope, but it's very, very easy to analyze. As you start to add revolute joints in, things become a lot more difficult to analyze, but not that difficult from the point of view of this module. So this is an example of the simplest robot that we will analyze, and this is a Cartesian robot, so it moves along 3 axes, X, Y, Z, okay? And as long as you know how much each axis has moved, so if it was 10 in X, 10 in Y, and 10 in Z, and you knew your start position, you just add in 10 to each coordinate of your start position. So there's nothing really difficult about analysing that robot to position it in space. So they typically use things like biological sampling. This is moving hard drives around in and out of specific places, or sample sets moving out of specific places within a test setup. Right, I'm going to break there for 10 minutes, and I'm overheating, and then I'll come on to the cylindrical robot. So if you want to stretch your legs, do something. If you can be back here by 4 o'clock to continue. Thank you. The robotic system has 3 actuators. They're all prismatic joints. So the actuators move along 3 orthogonal axes, X, Y, and Z. Makes the robot very easy to analyze, okay? Which means it creates a work envelope that's kind of a cuboid volume underneath the robot arm, okay? So you would move within this cuboid volume, okay? If we then start to look at slightly more complex systems, we introduce a revolute joint. So with the first one of these is a cylindrical robot. So it has a revolute joint, so it has a central shaft that has a revolute joint at the bottom that allows this whole arm to move around its axes, okay? And the arm is 2 prismatic joints, one to move it up and down vertically, and the other to move it in and out horizontally, okay? So the arm will move up the central axis, up and down, and in and out, and it creates this cylindrical volume, okay? Most work envelopes for robotic systems will have this area in the middle around the robotic manipulator that has a void. It's an area the robot can never reach into because the mechanism is in the way, okay? So I can't reach inside myself, or possibly could but wouldn't want to. So because my body is in the way, it's the same for a robot, the mechanism is in the way. So most robotic systems and their work envelopes will have this void in the middle that you can't reach into, okay? So cylindrical robot, 1 revolute joint that allows it to revolve around a vertical axis, and 2 prismatic joints. We have a polar or spherical robot that has 2 revolute joints and 1 prismatic joint. Again, it has a revolute joint that allows it to move around the vertical axes, but it has another revolute joint that's out in this axis that allows, this is very difficult now for me to do, so imagine this is a revolute joint, allows me to move around an axis that's coming horizontally out towards you. Okay, so I can rotate my arm up and down and also round my center axis. And that creates a spherical volume. Okay, so cylindrical robot, cylindrical work envelope, spherical robot, spherical work envelope. Again, has a void in the center around the manipulating mechanics. Then we have a SCARA robot. So why SCARA? It stands for Selectively Compliant Articulated Robot Arm. So it's a particular type of robot arm that we're going to talk about a bit more when we come to analyze it. But this has also 2 revolute joints. Revolute joint vertically that allows the whole of the arm to rotate around the axis. This is the fixed base. And then there's a link at the top of that rotating joint. And at the end of that link, there's another rotating joint here that essentially, so this link here is my upper arm. This link here is my forearm. So the SCARA robot moves its arm kind of that way, so rotating joint vertically here and one here, but also allows it to move all the way around as well. And it's a more or less cylindrical work envelope, again, with this void in the middle. So it has one revolute joint. At the end of here is a prismatic joint that allows it to reach in and out of its work envelope. Typically they're used for fastening down bolts, screws into workpieces. So this would be a kind of a screwdriver element, so it'd have a mechanical, electric screwdriver at the end, but it would push, using a prismatic joint, the screw or a peg or a bolt into a workpiece. Okay. And then articulated robot arms. So this is the most complex and probably the most common robot thought of in terms of an industrial application. So this will have all rotational joints, all revolute joints. So one on the base again that allows it to move around a vertical axis, and then you think about it, especially in the next slide, as a human arm, a revolute joint here, that's the shoulder, revolute joint here, that's the elbow, connected to our forearm, and then we have the wrist at the end. So each joint is considered or called an axis, and for a fully articulate robot arm in an industrial setting, you'll have 6 axes of movement. You'll have 3 axes that are the major axes, which are the kind of the 2 at the shoulder and the 1 at the elbow. So 3 major axes. Then you'll have 3 axes of movement around a fully articulated wrist that will be called, or we'll use the term minor joints. Okay? So the major joints allow me to position a wrist anywhere within my work envelope. And did I say minor or major then? The major joints allow me to position my wrist anywhere within the work envelope. The minor joints allow me to orientate whatever my wrist is attached to or holding. Okay. And it gives quite a flexible work envelope from the point of a fully articulated robot arm. And then there are various other types of configuration of robot arms. So this is a Delta robot. We're not going to focus too much on it. It's just a further example. But it's very good for very quick, rapid pick-and-place operations. And that's made up of totally revolute joints. We won't focus on that from an analysis point of view at all. So robot specification, what you need to define or decide when you're specifying a robot for a certain activity, a certain production process, etc., is number of axes, which give you the number of degrees of freedom of the robot. I'll go on to elaborate on what these mean. Capacity and speed, how much do you want to lift, how quickly do you want to move it. Reach and stroke, so how far does your robot have to reach. And I'll explain what stroke is in a few moments. Tool orientation, is it important to be able to orientate the tool at all, or can you just work with it in one fixed place and you never have to orientate it? So do you need a fully flexible wrist, or can you just have a fixed wrist and your tool orientation is always, say, vertically down? Repeatability, precision, accuracy. Can you always hit the same point? Can you hit the same point with a certain precision, and can you accurately hit that point as well? And again, I'll define some of these terms a bit more. Again, classic exam type questions, possibly, maybe, no promises. Number of axes determine how the robot moves, how the work envelope looks. Since robotic manipulation is done in 3D space, 6-axis robot is the most general, most flexible robotic manipulator. In the sense it can move its tool to both an arbitrary position and an arbitrary orientation within its work envelope. So if you want to be able to position this tool anywhere within my reach, anywhere within my work envelope, and be able to point it in any direction, you want the most flexible approach, and that would be a 6-axis robot. So it has 3 axes of movement, which are the major axes, 3 axes of movement, which are the minor axes. So axes 1 to 3, major, position the wrist, already said. Axes 4 to 6, minor, orientate or orient the tool with respect to your workspace. If you have more than 7 axes, such as if you think back right to the beginning, where I talked about this kind of flexible worm-like robot that has many, many degrees of freedom, okay? The degrees of freedom above 6 give you an ability to move around obstacles, Okay? So if I had a 6 degree of freedom robot, I can move my wrist anywhere within my work envelope and orientate my tool, okay? And I could reach a point here and point downwards. If this was an obstacle in the way, I can't go through it, I'd have to go around it, but the manipulator as set up won't allow that. So maybe I have to introduce another joint in the middle of my forearm to allow it to bend around to reach the point. So I'd introduce another joint, another degree of freedom. Okay? So that's anything 7 and above allows you to move around objects. So example, Scarra arm. So we have a revolute joint, so joint number 1, axis 1. Joint number 2, another revolute joint, so these both have vertical axes of revolution that we move around. Joint number 2, so major joint number 2. And joint number 3 is a prismatic joint that allows this tool holder to move vertically up and down. Okay, so the first two allow it to move around, 2 rotational joints, and the last one allows it to move up and down. You can have a 4th axis. If you have a screwdriver, you could consider that to be another axis where you have a rotational joint that will drive the bolt, the screw, into the workpiece. Okay. An articulated robot, first joint, that's the one where you have vertical axes and you have to rotate around the horizontal plane around that axis. Then you have second axis that's now orthogonal to that one, so think of that as your shoulder. Okay. Yeah, and then third, which would be my elbow when comparing to my arm. So they're the 3 major joints, and those joints allow this at the end to be positioned anywhere in space, well within the work envelope constraints. 4 on this robot, well I got 4, 5, 6, is 3 joints, all at 90 degrees to each other that give you a fully flexible wrist. Okay. There's a bit more detail on the wrist. For the purposes of this module, I will, for the most part, stop at the major joints. I won't consider the minor joints, okay? Because you will just be repeating the same analysis for that. And just to keep it sensible in terms of an examinable question, we will just focus on the major joints. So we will consider the robot arm up to the point where you mount something on the end. So we won't consider the actual analysis of the wrist, okay? So just to let you know that up front. And this is just an example of a redundant joint. So the robot arm may not have had that joint in, but it could still move the tool anywhere in the workspace. But because we have an obstacle in the way, we need to introduce this joint so it can reach into the void, protected by that obstacle. Degrees of freedom, I kind of touched on or mentioned these, and degrees of freedom required to define a minimum number of independent parameters, variables or coordinates we need to describe a system completely. And for us, robotic manipulators are designed to work within a 3D space, a 3D volume, with 6 degrees of freedom. So what the degrees of freedom for us will be, 3 translation, so up, down, backwards, forwards, left, right, and 3 rotation, which yaw, pitch, and roll. So the 3 major joints, so configured for a fully articulate robot, the 3 major joints, I think of that as my shoulder and elbow, will allow me to move in, say, X, Y, and Z. So I can move my wrist to any point along X, Y, and Z. And that's the coordinate system we'll be using. When I want to orientate my wrist and orientate my tool with respect to the work envelope, I bring in the 3 rotational elements, the yaw, pitch, and roll, and these are terms applied to how the wrist moves, and it's similar to an aircraft movement or in flight. So you'll have the, always get this wrong, the yaw, which is rotation around the vertical axis, the pitch, which is nose up, nose down, and then the roll, which is left to right, right to left. Okay? But the 3 translational degrees of freedom allow us to position the end effector. The 3 rotational allow us to orientate the tool with respect to our work envelope. So degrees of freedom defined as a minimum number of independent parameters, already said that. So for example, how many degrees of freedom are required to describe a point in 2D space? or a rigid body in 2D space, a point in 3D space, a rigid body in 3D space. What do I do next? Right, okay. So what we want to do, if we want to describe any of these, we will need a number of degrees of freedom, a number of independent parameters to describe that situation. Okay? So degrees of freedom, point on a 2D plane. We require 2 degrees of freedom, so 2 translation parameters, one along the horizontal, one along the vertical, and that's just a point. If we change the point to a body, a rigid body, we have the same translational parameters, but we also have an element of rotation. This all happens on the plane of the board, an element of rotation. So how is this rigid body orientated with the plane of the board? Okay, or in the plane of the board, sorry. So we have 2 translations, 2 degrees of freedom here, 2 translations, 1 rotation, 3 degrees of freedom. We can move horizontally, we can move vertically, or we can rotate this. Point in 3D space, we're just extending this now by another dimension, so we can move along one axis, another axis, and another axis. Our axes for this module are always orthogonal, so that's 3 degrees of freedom, because we have 3 translations. If we have a rigid body, we can also include in 3 dimensions 3 rotations as well, and the rotations would take place around each of these axes. Okay, so you have translation along each of these orthogonal axes, or you can have an amount of rotation around each of those axes as well of this solid body to fully describe how this solid body sits within a 3-dimensional space. So that would be 6 degrees of freedom. So back to the earlier example, so I have a rigid body, 2 dimensions. It has 3 degrees of freedom. Translation, it can rotate. We don't have that situation within our robotic systems, and we normally, our joints that we put into our robotic system will apply constraints that limit the number of degrees of freedom. So what I'm going to do here, I'm going to apply a joint that fixes the bottom end of my rigid body to the ground, to a workspace, work area, through a rotational joint. The axis of rotation is out of the board towards you, and so that link, this rigid body, can now only move around that joint. Okay? It can't move along this axis, it can't move along this axis, it can only rotate around that joint, so it has 1 degree of freedom. Okay, does that make sense? All happy with that? Yeah? Okay, this is a graphic just to compare, because I do a lot of this hand waving stuff, talking about my shoulder joints, my elbow and everything. This is just a graphic to illustrate how a fully articulated robot resembles kind of the human arm. So it's worth having a look at, and I've got no issues if you're in the lecture and you're moving your own arm around and everything. I'm also going to give you some widgets at some point as well that represent the coordinate systems that we work within, because we always work within a specific coordinate system, which is a right-hand orthogonal set. Okay, so I will provide kind of aid memoirs for you that you can also take into the exam, so you don't get confused and use the wrong coordinate system. Where are we? So again, possible exam question is, given a robotic system, you might want to calculate the number of degrees of freedom of that robotic system. There's an approach to this using something called the Grubler's criterion, and we will work out the parameters of that robot system, drop them into the formula that's specified here, and that will give us the mobility or the number of degrees of freedom of that robotic system. So the elements here, we have CI. So CI is the connectivity of the ith joint. 2D system has 3 possible degrees of freedom. So we have the 2 translation and the 1 rotation of a solid body within that 2D environment. Okay? And if we apply a constraint, a number of constraints within that, and limit how the rigid body can move by putting a joint in place, as the previous example, we apply a number of constraints at that joint. Okay, so for the example previous, where we had the general case of the rigid body moving on a 2D plane, 3 degrees of freedom, we put a joint in, it has 1 degree of freedom, we've applied 2 constraints. We've stopped it moving in the translational dimensions, and we're only allowing it to rotate, so we've removed, or we've added 2 constraints. So this would be total degrees of freedom of a rigid body in a 2D situation would be 3. Number of constraints imposed by that revolute joint in the previous one would be 2, and then we drop these into our formula here, and once we work this out for that, it will give us a number of degrees of freedom. So you can try that for the previous example if you want. So that's known as Grubler's criterion. Again, it's something that could come up in an exam. One example, I'm going to do this in a later lecture, not now, but you may want to look at it and kind of test yourself out whether you can do that at the moment. Okay, so we have number of links in 2D, so this only moves in the plane of the board. You can work out what's going on along it, apply Grubler's criterion, try to come up with the total number of degrees of freedom for that robotic manipulator. That was for 2D situation. We can move into 3D. In general, a rigid body in a 3D environment will have 6 degrees of freedom. We can apply constraints in the form of applying joints between our links, as we did previously, and that will apply a number of constraints. Okay, so connectivity of each joint would be 6 for a general 3D situation. Number of constraints, and we will, for the robots we're looking at, we'll always apply 5 constraints. So we'll always reduce it to just 1 degree of freedom at every joint. Okay, so revolute joints, prismatic joints only have 1 degree of freedom. They either move along a linear path or rotate around one axis, so only 1 degree of freedom. Okay, so you can again drop in those numbers and come up with the total degrees of freedom for a 3-dimensional, robotic arm that operates in a 3-dimensional workspace. Okay, so it's a slight difference here to recognize that we've moved into 3 dimensions. Reach and stroke, measure them, so you need to understand these elements. You need to understand how your robot will move within the work envelope and where it can work within the work envelope. And reach and stroke are a rough measure of the work envelope. Horizontal reach is defined as the maximum radial distance from the center, the fixed point of the robot, outwards. So think of it, a boxer has a reach, that's the furthest a boxer can hit you. It's determined by the length of the arm, and that's similar to a robot. Okay, so reach is the furthest it can extend to, the furthest extent of the work envelope. Horizontal stroke represents the total radial distance that can move. So from my center point, my arm can't move to my exact center point from this position. So my stroke is from here out to the extent of my reach. So the stroke is always less than reach. Okay, so the reach would be measured from my center point out to the end, but stroke is measured from here out to the extent of my reach. Okay. So you have concepts of both horizontal reach and stroke, and also vertical reach and stroke. Repeatability, precision, accuracy, I've already talked about these. The repeatability is a measure of the ability of the robot to position the tooltip at the same place. There will always be some error, okay? So it will never hit the same point all the time. There will always be some small error. And precision is a measure of the spatial resolution with which the tool can be positioned. Your robot configuration may allow you to hit that point, but because of my actuator, my joint, one slight movement will mean the next point I can hit is here, and I can't really hit anything here. It just depends on how the actuators work. There may not be an infinite set of points between these two it can reach. It may be, I can do this, move 1 degree, which is the smallest I can move with my rotational joint, and that puts me here. Okay? Does that make sense? So it's spatial resolution. So how close can I hit points within my work envelope? And there's just a bit of a graphic to represent those. So accuracy, how close am I going to get to my point? Precision is the spatial distance that I can, the minimum spatial distance I can hit adjacent points. And repeatability, if I want to repeat hitting point A, how close will I be at every attempt? Okay. The precision for robots will depend on its configuration. Cartesian robots, horizontal precision, vertical precision is uniform, so it can hit points in space uniformly distributed. As you introduce rotational or revolute joints, that changes it a bit. So cylindrical joints, moving up and down along a vertical axis, so along a prismatic joint, you get this uniform precision, so you're just moving in a linear fashion. When you start rotating around the central axes, and just think of it, if I rotate 1 degree, but my arm is here, I'm going to move a distance, okay? Okay, if I have a longer arm, or extend my arm, that 1 degree movement is going to give me a bigger distance. So that decreases my spatial resolution as I move away from the center point of my robot. Does that make sense? Happy with that? Yeah. So just a bit of a graphic to represent those. Precision versus accuracy. Highly precise, we're hitting the same point in space. Not so great in accuracy because we want to really hit the center. Accuracy, but not too bad. We're all clustered around our target point. Precision, but they're all over the place, so not very precise. Excuse me, guys. Low precision, low accuracy, all over the place, away from our target point. Very precise, very accurate. We're basically clustered around where we want to be. Okay. Capacity and speed. I'm not going to worry too much about these. David might dip into these when he talks about dynamics a bit more. But here we are really considering load carrying capacity. How much weight do you want to move? How quickly do you want to move it? How quickly do the tooltip need to move? Not really interested in this from my part of the module. But both are very much application dependent. What you may be asked in the exam is to think of an application and say if these are important to you. It could be you're lifting an engine block with a robotic system that weighs a lot more than lifting a small box containing plastic bottles. Okay? And so the load and capacity considerations will be vastly different. Well, I finished. Excellent. Thought I'm going to pass out. So that's the background to robots, why we use robots, how robots are configured. I have gone through it quite quickly, but it does account for the best part of the first question in the exam. So it's stuff you'll need to know when you will be asked questions on it. Next week, I'm going to move into kind of the more mathematical aspects. Have I still got that? If you just bear with me for a second.